All right, guys. In this video, we're just going over the 7-3 VLO practice test. Okay, um, so this is all the stuff that we need to be able to do with basically delta H, different calculations we can do with it, and then also uh, specific heat capacity. So, using the delta H of a reaction in just basic stoichiometry questions, what the value of delta H means in terms of if it's negative or positive, um, and then calculations to figure out how much heat is required to melt something or to vaporize something, or how much heat is released when something condenses or something freezes, or calculations on with specific heat capacity, like how much energy is going to be required to increase the temperature of this much water from this temperature to that temperature, right? So, the different types of calculations you could kind of do, when you map out a heating curve, those types of calculations. And then just really, what does a negative enthalpy change mean? What does a positive enthalpy change mean? And all that good stuff. Okay. So we're going into that. All right. So here in number one, they give us this kind of setup. They say when 2 moles of benzene burn in oxygen, that's how much energy is released. Okay. But, so they could have just given us this, and that's telling us this much energy is released for every 2 moles of benzene that combust, right? That's really all we needed. Now they give it to us in a nice balanced equation. So, right, we have our recipe, and now we have a little bit more information about our recipe, right? So that's the balanced chemical reaction. We know it's a combustion reaction, and this is the delta H, the enthalpy change for the reaction. So the first thing to note is that delta H is negative, so that means we know it's an exothermic reaction. Now remember, combustion is always exo, okay? But if this were a different type of reaction and delta H were a positive number, then that would be endothermic. So part A, all we had to know is that it's an exothermic reaction, because you could say delta H is negative. That means an exothermic process, or what it really means is that much energy is produced. Okay, that much energy produced. But another way to interpret this is, again, exactly what was said in this statement here. This equation is showing this much energy for 2 moles of this that react. Okay, and so we can use this energy value and the coefficient, which is moles of benzene, right, to be a conversion factor to go from energy to moles of benzene, or moles of benzene to energy. And we could use the coefficients of everything else in the equation with this delta H value and do any type of stoichiometry we want. So really, the delta H of a reaction can be our conversion from moles of something that's a part of the reaction to total energy, or total energy to moles. Okay. And so that's what we have to do in part B. Okay. So we want to know how much benzene we need to burn if we want to produce this much energy. And we want to know how many grams of benzene. So again, we're given an amount of energy and we're asked to find the mass of benzene. That's stoichiometry, right? Given the amount of one thing, energy in this case, find the mass of benzene, a different substance. Stoichiometry. So we follow our steps. So step one, take what we're given. Well, our recipe is given, step one. Step two, take what we're given and convert it to moles. So how do I convert energy to moles? Well, I have to use my recipe, right? And so I know 2 moles of benzene for every 4,575 kilojoules released. So if we take the total energy that we want to produce and we divide it by the delta H of the reaction, but then we also have to multiply by the coefficient of benzene, that'll tell us how many moles of benzene we have to burn. And then we just have to multiply by the molar mass, and they were nice enough to give it to us, so we don't have to worry about calculating it, but we could if we needed to. And that would be the setup. So if we want to produce that much energy, we need to burn around 850 grams of benzene. Okay. In part C, just another stoichiometry setup. This time we're given an amount of oxygen. Okay, so if we go back up to our equation, it takes 15 moles of oxygen to burn in this reaction to produce this much energy. It only takes 2 moles of benzene to produce that much energy, but it takes 15 moles of oxygen to produce that much energy. So here we're going to use the delta H of the reaction, but it's going to go on top, and 15 moles of oxygen is going to go on the bottom. So we're going to use that ratio to go from moles of oxygen to total energy produced. Okay, so the first thing we have to do is take the liters of oxygen and get it to moles. So because we're at STP, we can use that shortcut. If we weren't at STP, they'd have to tell us what the temperature is and the pressure is, so we could use the ideal gas law to figure out moles of oxygen. And then once we had moles of oxygen, then we got to multiply by our mole ratio step, our delta H mole ratio step, right? So liters will cancel out, and we left with moles of oxygen. And be careful, right? Now that we have these weird ratios where, you know, neither number on top or bottom is 1, right? We're used to, 1 mole for whatever, right? We're used to having, one of the numbers in our ratio to be 1, right? And it's not always the case. So what do we have to do? We have to multiply by that, but then we also have to divide by 15. A lot of people forget to divide by 15, right? But that'll cancel out moles of oxygen and give us our total energy. And again, we should be thinking about sig figs. This energy value only had 2, so that's why part B had to be 2 sig figs. And then again, this volume only had 2, and so that's why we had to round to 2 sig figs there. You can put it in scientific notation if you want it, like, so 3.4 times 10 to the 4, but that would be the right number of sig figs. All right, so this one, we want to know, how much energy is going to be released as HCl freezes. Okay, so first off, we got to understand, like, in this question, they give us these 2 values for for HCl. They give us the heat of vaporization for HCl, and they give us the heat of fusion. What we got to remember is we would only use this if we were talking about energy absorbed or released, when we're talking about boiling, absorption of energy, or condensing, releasing the energy, right? And we use this for melting or freezing. So because we're talking about freezing here, we need this value. We don't need that value, okay? So we know that we're going to use this value. And what does it say? It says this much energy to melt 1 mole of HCl, okay? So do we have 1 mole of HCl? No, we got 75 grams. So what do we have to do? We have to convert grams of HCl to moles. And then this value is, energy required for 1 mole of HCl melting. But if we made that negative, that would be energy released when 1 mole of HCl freezes, right? Which is the opposite process of melting, right? If the forward process is endothermic, the reverse process is exothermic, right? So we know melting is endothermic, positive delta H. We know freezing is exothermic, negative. It's still the same value. It's still the same amount of energy. It's just, is it being absorbed by the HCl or is it being released by the HCl? In this scenario, it's that much energy that's being released by the HCl as it freezes. Okay. Now, we don't need the negative sign for this answer because the question was how much energy is released, and we're reporting the amount, right? If this says what's the energy change instead, that's when you would have to make that negative to know that it's energy lost by the HCl sample to the environment, not absorbed by the HCl sample, right? That would be if it was melting, okay? Now, if we change this to, condenses, then the only thing that changes is we're putting this value here. It's still the same idea, but this is for boiling, vaporizing, or condensing, and this is for melting, freezing, okay? All right, so on the back, we got basically a Q equals MCAT question, right? So we got specific heat capacity, we have mass, and we have the initial temperature, and they give us the total energy. So this question is, we have to use this equation, but we're solving for the delta T, right? We have the energy, Q, heat, enthalpy, H, Q, they're all the same thing. So we have that, that's this value here, that's how many joules we have. We have the mass, right? And remember, C is the specific heat capacity, and that's this value for copper. And so the question is, if the copper sample absorbs this much energy, what will its new temperature be? How how much will the temperature increase, right? So we're solving for delta T. So we know Q equals MC delta T, but we're solving for delta T. So it's Q, energy divided by mass, also divided by specific heat capacity. So we'll take our energy, put it on top, we'll divide by 50, and we'll also divide by 0.39. And that comes out to be 282. Now, that's not our answer. That's the delta. That's the change. Okay? So if our initial temperature was this, and if we absorb energy, our temperature is going to go up. So once we calculate delta T, what do? We add it to the initial temperature, and that is our final temperature. Okay? Now, the other way you could do it is, since we know the initial temperature, remember delta T is really T final minus T initial. So if you wanted to, you could put that in parentheses, T final minus T initial, and plug in T initial, and then you're just solving for T final. It's just a little bit more, I don't know, slightly more time consuming, because I guess I would say it's going to be, you got to distribute through, right? It's going to be a little bit more algebra you have to do. So I think the easiest thing to do is solve for the delta T, and then at the end, add it to the initial temperature. Now, be careful. We could do the same thing, but we could be losing that much energy and the sample be cooling down. And if it was that much energy released, then your delta T would be negative, and you would do the initial temperature minus the delta T to get your new temperature, right? If it was cooling down. But in this scenario, it's heating up. So calculate delta T, add it to 25, the initial temperature, or whatever the initial temperature was. In this case, it was 25, and you get your final temperature. Okay. All right. In this one, they give us a potential energy diagram for a reaction, and it's for this reaction. Okay, so notice that this reaction is the decomposition of ammonia. So this is where we got to be careful, because when we look at number 4, they try to trick us. Okay, as soon as I see this diagram, I know that the forward reaction is endothermic, the reverse reaction is exothermic. Okay. All right. So the decomposition is endothermic, but the synthesis would be exothermic. Okay. And remember, if we read it from left to right, this is the enthalpy or energy of the reactants, and this is the products. And remember, delta anything is final minus initial. So the delta H of a reaction is products energy minus reactants energy. Okay, so this minus this, and that would be the forward reaction. Okay, so that's our delta H. And if we're talking about the forward reaction, it's a positive 80 kilojoules. And if we talk about the reverse reaction, it's a negative 80 kilojoules, but it's still the same value. Okay, so according to the chart, would the synthesis of ammonia be exothermic or endothermic? Well, the decomposition is endothermic, so that means the synthesis is exothermic. We're talking about the reverse reaction. Okay, we just said the delta H, it's the difference between this value and this value. It's just, is it positive or is it negative? So in this case, the forward reaction is positive. Okay, and then remember, what a catalyst does is it lowers the activation energy. Okay, and so this line right here would represent what a catalyst does, lowers the activation energy. Okay.